And welcome back to SanfordFlipMath. This is AP Calculus, section 2.4 in our regular calculus book, which is Calculus, Graphical, Numerical, Algebraic by Finney, Demana, Kennedy. I just mentioned that because of copyright issues, because some of the stuff in here is taken right out of the book, like some of the definitions and things. Just a speedy recap from section 2.1, and if you need more information, go back to 2.1, see the video for that, which is about average rate of change and instantaneous rate of change. Just a reminder that average rate of change is some overall change in quantity versus some overall change in time, and basically it's the slope of the secant line, and it's sloped like Algebra 1. So it's whatever that y quantity change was over whatever that x quantity change was. You need 2 points. You need an x and a y and an x and a y. Okay? And just a reminder that instantaneous rate of change is that rate of change, and it's again like slope, as is the case for average rate of change, but this is the slope of a curve at a single point. Slope of a tangent line. It is the instantaneous rate of change. It's the rate of change right now. Okay. In our book on page 90, this is what the equation looks like. And this is actually a peek at chapter 3. They adjust the equation a little bit, and just so you understand what's going on, this is just a specific x value, and this is for any x value. And so what I've recommended us doing is let's just do this now, and then if we need to, what that lets us do is if we needed to calculate slopes at more than one point, then we can do that without having to redo the whole difference quotient, the whole hoopla. Okay, this is what it looked like back in section 2.1. Okay, and I just have it here so to remind you that yep, we actually did that. And instantaneous rate of change, and this was an example. Okay, and look at that cannon. Wow, that's some good art there. And so feel free to go back and pause this video at any point in here to see what went on back in section 1, or you can certainly go back to that video if you need to. Okay? And I'm ignoring that little police guy on the right saying stop, because it is time for us to go. Okay? Here are some synonyms for average rate of change, and again, I'm going to abbreviate that like this, and our little formula is again just like back in Algebra 1. Okay, and these are some synonyms. Cinnamon roll would be good right now if I had some coffee to go with it. This is instantaneous rate of change, and again, the formula for this, limit as h approaches 0 of this big ugly slope formula, and the idea is that again, the h is how far apart the x values are. So this is the y value at 1x, this is the y value at another x, and what we're doing is making those x's become closer and closer together. You might have noticed there's a link on SanfordFlipMath now to an animation about average rate of change, slopes, and derivatives. And it's all about this, and that actually is kind of informative. It'll give you a better conceptual understanding. It's worth taking a peek at. Not mandatory, but I think it's worth it. That's why I put it there. Isn't that clever of me? All right, we're going to do some examples, and we're going to take this for a spin. And my only real concern in all of this is context. And sometimes it's little foo-foo algebra kind of stuff that we have to watch out for. Okay, so I'm going to do an example similar to the first few that we'll be working on in class. And so I'm going to just give you a function, let's say 2x squared plus x. And then what I want to know is the average rate of change on the interval between -1 and 2. Okay. Average rate of change, remember, is slope. Slope like back in Algebra 1. So this is actually a problem that, if you kind of talk through students with the notation, they could actually do. Now, if that's an interval, then this is an x and this is an x. So that means we're going to write some ordered pairs. Okay, got to have ordered pairs to do this. So -1 something. And so if I do -1 squared is 1 times 2 is 2 plus -1 looks like 1 to me. Okay, same song, second verse. 2 squared is 4 times 2 is 8 plus 2 is 10. So the slope then is going to be y2 minus y1 over x2 minus x1. And that's looking like 3. Okay, that's it. Okay. Now, so that kind of handles all of the problems at the beginning. Now keep in mind that if there are trig functions in there, remember anything we do trig in calculus is in radians automatically. Okay. In terms of estimating slope, slope from a graph, and you can take a peek in the book for this, all you're going to do is kind of focus in on individual points and look at rise over run. Okay, and that's all I'll say about that right now. We'll say more in class probably. Okay. Next up, what I'd like to do, in fact, I'll just go to the next page. We're going to look at another example. And so I have a function, x squared minus 4. And what we're going to do is find the slope of the curve at, let's do x equals 1. We're going to find the equation of the tangent line at x equals 1. We're going to find the equation of a normal line at x equals 1, and we'll do a little graph for all of this so we understand what is going on. Okay? Okay, so if I want the slope of a curve at a point, that is just the same thing as instantaneous rate of change. That's what that is. So we're going to do the limit, okay, and we're just doing the big ugly thing. Okay, so following along here, we're just going to substitute, and what I would recommend, and I always recommend this, when you're substituting stuff in, what I often do is I'll go through and write down parentheses for my x. Okay, now for this next part, x squared minus 4, I don't really have to substitute anything for x, so let me pop back here. I'm supposed to be doing f of x plus h, so this is x plus h. Now, just so we're clear, this is this in this formula. Okay, and then let's see how green works. This is this part. Okay, and I still need a little h on the bottom. Okay, be especially careful if there's more than one x that appears in the original function. This one's not too bad. Okay, limit as h approaches 0. Now again, I'd prefer to not put the 1 in and do 1 plus h, because if I need to do multiple calculations with this thing later, I'd rather have an x there. Okay. All right, so I need to distribute this out. That's really x plus h times x plus h. And we've done that part enough. It's probably familiar. Okay, so this is all of the first one. And I'm going to go ahead and distribute that negative. Okay, so 4. Okay, and I'm going to go ahead and do a little combining of like terms. So x squared minus x squared, goodbye. Negative 4 plus 4, goodbye. So this is now 2xh plus h all over h. Well, that's not so bad. Okay, and we just got a couple more things to do. Okay, did I miss something here? Nope. Oh yeah, that was h squared. All right, for those of you following along at home, this is h squared. Okay, so that was right there. I knew that the h's need to really go away here in a minute, so that was my clue. Okay, so the limit as h approaches 0. Okay, and again, I'm just going to divide out this common factor of h. Oh, I don't need that fraction bar. I just got a little excited there. So 2x plus h. Okay, so now I'm to the point where there's no h in the bottom, so I couldn't just substitute h in because that would make it undefined or indeterminate. And so now I can substitute the h in, and this is just 2x. Okay, so if you recall, we could call this f prime of x is 2x. If you want to call that y prime, that's good. We want to know f prime for when x equals 1. So that's 2. Okay. Okay. What we need to do now is put this to use. Okay. So quick little note here. We did that. Slope of the curve we said was 2. Okay. Now we need the equation of the tangent line. Okay. Well, a tangent line is a line that's tangent. Isn't that clever? It's tangent to the curve. Well, I know the slope of the line tangent to the curve. That's just f prime, or in other words the derivative, or in other words the instantaneous rate of change. It was 2. I'm finding this at the x value of 1. Well, in order to write the equation of a line, I need to know the slope and a point. Kind of a big fan of point-slope form of the equation of a line. Just why? Because it's easy to work with. I know some of you are diehards on the slope-intercept form, y equals mx plus b, and you're certainly welcome to do that. And I may or may not do it myself. We'll just see how it goes. And so remember, the equation was x squared minus 4. That was the function that we're looking at. Okay, so, and this is for f of x equals x squared minus 4. Well, this is an x value. This is a y value. Y values come from y. So if I take this 1 and put it in here, 1 squared is 1, minus 4 is negative 3. Well, I need a slope and a point. I guess that's it. I just need to put this bad boy together. Okay, so if I do point-slope form, y minus y1, well, that's a minus a negative 3. I'm going to call that plus 3, equals slope times x minus the x value. That is the equation of the tangent line. Now, again, I know some of you are looking at that going, ugh. So if you want to do slope-intercept form, you can. And so I would substitute in negative 3 for the y value. We know the slope, the x value is 1. And so 2 times 1 is 2. If I subtract 2 from both sides, that's b. So this would be y equals 2x minus 5. Again, this is the equation of the tangent line. These two different versions of it. If it does not specify a form, then it doesn't matter. If it specifies a form, again, this is point slope. This is slope-intercept. Okay, sometimes it'll be a multiple choice question and you have to pick the correct question. You have to pick the correct one and you won't have a choice as to form. Okay, so this is, if I go back here, this is the slope of a tangent line. Now, you may or may not recall that a normal line is a line that's going to be perpendicular to the tangent line. Okay, so if I want to write the equation of a normal line at x equals 1, okay, then the point's still 1, negative 3. The normal line will have a perpendicular slope to the tangent. So the slope of the tangent line was 2. The slope of the normal line, which is perpendicular, has to be the opposite reciprocal. So I have to do the opposite sign, so it's going to be negative, and I have to do the reciprocal number, so it means I have to flip it. So it was 2, so now it's 1/2. Okay, so I'm going to use this slope now. So if you use point slope form, this is a big, no big deal at all. Y minus negative 3, so plus 3, equals negative 1/2 times x minus 1. This is it. Now if you're going to do slope-intercept form, you're going to end up using the f word, fraction. I know you guys were thinking bad words, and that wouldn't be me. Okay, and you can either rearrange this one, or you can substitute in at the beginning. So like, for instance, again, we're doing y equals mx plus b. So negative 3 equals negative 1/2 times 1 plus b. So negative 3 equals negative 1/2 plus b. Add 1/2 to both sides. So this is negative 2 and 1/2, also known as negative 5/2, whichever form you prefer. So y equals negative 1/2 x minus 5/2. So again, this is either of these are the equation of the normal line. Okay, and let's just do a little sketch here of what's going on. Okay, so 1, 2, 3, 4. Here is y equals x squared minus 2. Oh, I missed. Or minus 4, I'm sorry. This is y equals x squared minus 4. Okay, at x equals 1, we said earlier the y value was negative 3. Here it is. And if we draw a line here, this is that line, y equals 2x minus 5, also known as y plus 3 equals 2x minus 1. Okay, this is the tangent line. Remember, a tangent line touches the curve in a single point, that single point being down here, the one that we found, okay, at x equals 1. Okay, normal line is perpendicular to the tangent line, and there's always a scale issue, so perpendicular on your calculator may or may not look perpendicular. Okay, and that one is y equals negative 1/2 x minus 5/2, also known as this one. Okay, all right, and that is everything for that example. Okay, and I just want to do maybe one more thing, and then we'll be done with this craziness. And that's, word problems are always fun. So what we're going to do is let's find the rate of change of the area of a circle. This is similar to one of the problems in your book, number 25. When the radius of the circle is, let's do 2 centimeters. Okay, so I have this circle, and let's say the radius is changing, and what I want to find is as I change the radius, how does the area change? How quickly does it change? What's its rate of change? Okay, so you should be familiar with a cute little formula for the area of a circle, pi r squared. Worth noting that circumference equals 2 pi r is circumference. And just a reminder that if we're going to have square units for area, we have to square something, and that would be the radius. Okay, and so we want to know how fast is it changing as the radius is changing, and when that radius is 2. So what we're going to do is instead of dy dx, which is another way to write derivative or instantaneous rate of change, we're going to do dA dr, because it's instead of y and x, it's a and r. Okay, so now notice how many x values, or r values in this case, we have. We just have a single value, not 2. So we're going to be doing the instantaneous rate of change. So we'll be doing the limit as h approaches 0 of f of x plus h minus f of x all over h. Now obviously the f of x is really a of r, or area with respect to r. So here we go, limit h approaches 0. Okay, so I'm going to do pi times something squared minus pi r squared all over h. And that something is that x plus h, well, it's really r. Okay, so let me do a little fixage here. Okay, so it, again, should be r plus h. Okay, and I know some of you are just going to make those into x's, and that's fine. Okay, so this is a prime. This is how the area is changing. Okay, so the limit as h approaches 0. I need to FOIL or distribute this out, so it's going to be r squared to r h squared minus pi r squared. Okay, and you can see me writing. I'm just distributing now. Doesn't really matter whether that pi is in front or the 2's in front for that term. Okay, and we're going to combine some like terms. Pi r squared minus pi r squared. Goodbye. That's it for that. Now the only other thing is, I notice there's an h in common based on whatever, based on what's left here. Okay. Oh, somehow this plus magically became a minus. Let me fix that. Thank you for all of you following along at home. You probably just said that to me. Okay, so h, h, h. Yep, you heard the pun last time. Get the h out of here. So limit as h approaches 0, 2 pi r plus pi h. Okay, so now that the h is out of the denominator, I can, I couldn't do it there, but I can do it here. I can substitute now. So this is 2 pi r plus pi times 0, that's nothing. Okay, so this is how the area changes for any r value that we have. If r is changing, it works like that. Okay, so if I want to know the rate of change when r is 2 centimeters, then I'm going to do a of 2, a prime of 2, sorry, 2 pi times 2, so 4 times pi, and this is, let's see, so centimeters per centimeter? No, square centimeters. Now, so this is, okay, so this is the rate of change of area with respect to r. So this would be square centimeters per centimeter. So those go away, and we're just left with centimeters. Okay. Again, as always, feel free to rewind, go back front, divide. Rewind, pause, etc. And if you have questions, we'll see you in class. Thank you.